What is blockchain? Blockchain is an immutable, sequential chain of records called blocks, which contain transactions, data, or any other information we wish to store. These blocks are linked using cryptography. Each block contains a cryptographic hash of the previous block, a timestamp, and transaction data. Blockchains are designed to resist the modification of data and are an open, distributed ledger that can record transactions between two parties efficiently and in a verifiable and permanent way. The code block defines a basic struct in Rust for a blockchain's block. A block contains an index, a timestamp of creation, arbitrary data, the hash of the previous block in the chain, and its own hash. Implementing the block struct necessitates methods like new to create a new block and calculate hash to generate the block's hash, which ensures the integrity and chain connectivity of the blockchain. Each block's hash is calculated using its unique features and the hash of the previous block, ensuring that any tampering with the block's data can be easily detected, since it would require recalculating every subsequent block's hash. History of blockchain. The concept of blockchain was popularized with the introduction of Bitcoin in 2008 by an individual or group under the pseudonym Satoshi Nakamoto. However, its roots can be traced back to cryptographic advancements and concepts like timestamping digital documents. Let's outline a simple blockchain structure in Rust to understand the underlying principles. The code defines a block struct in Rust, which serves as the fundamental building block of a blockchain. Each block has a timestamp, its own data, a hash of the previous block, and its hash. Impl block contains methods for creating new blocks and calculating the hash. We are using the chronocrate for timestamping and MD5 crate for hash calculation. This simplistic representation serves to illustrate the linking nature of blocks within a blockchain, where the integrity of the chain relies on the hashes of previous blocks. Key characteristics of blockchain. The key characteristics of blockchain, which make it a revolutionary technology, include decentralization, immutability, security, consensus, and transparency and traceability. Let's create a simple Rust struct to demonstrate these properties conceptually. The Rust structs blockchain and block illustrate a simplistic form. A blockchain is a series of blocks, vec block, each containing an index, timestamp, and data with a unique hash and reference to the previous block's hash, previous hash. This structure promotes immutability and traceability, as each block's data cannot be altered without changing the entire chain's hash sequence, a key characteristic of blockchain technology. The add block function would be where new data is added to the chain, representing consensus and transparency. The verify integrity function represents the security feature, where the blockchain's integrity is checked, validating each block's hashes and ensuring they haven't been tampered with. Together, these structures and functions exemplify the core characteristics of blockchain in a Rust context. Types of blockchain. Blockchain technology can be categorized into several types depending on their access permissions and use cases. The main types of blockchain are public, private, consortium, and hybrid blockchains. Each type serves different needs and has unique characteristics. Let's explore a simple Rust code snippet to demonstrate categorizing blockchain types based on their level of access control. The Rust code defines an enumeration blockchain type, which categorizes blockchain into 4 types: public, private, consortium, and hybrid. The function blockchain type description takes a blockchain type as a parameter and returns a description of the blockchain type. A match statement is used to associate each blockchain type with its respective description. This demonstrates how each blockchain type has a distinct level of access control and governance, which can be described and differentiated within a system. This code isn't actually creating a blockchain, but a fundamental concept needed to understand before implementing a blockchain in Rust. History of Rust. Rust is a systems programming language that aims to provide memory safety, concurrency, and performance. It was first designed by Graydon Hoare at Mozilla Research. The language grew out of a personal project of Hoare's, which he started working on in 2006. Several years later, Mozilla began sponsoring the project, and they announced the first official version of Rust, 0.1, in January 2012. Rust has since grown and evolved, being influenced by languages like C++, Haskell, and Erlang. It was built with safety and speed in mind, aiming to be a language that could provide the low-level control of C++, but with a greater emphasis on code safety. One of Rust's most distinctive features is its ownership system, which helps manage memory safety without the overhead of a garbage collector. While the topic of the history of Rust doesn't necessitate a detailed code example, it's important to recognize the environment Rust emerged from. As a systems programming language, Rust addresses issues of memory safety, parallelism, and performance that are critical in system-level code. Its development was heavily community-driven, with an open-source community contributing to its standard library and tooling ecosystem. Rust's compiler, Rust-C, uses the LLVM as its backend, which enables it to generate highly optimized machine code. An understanding of Rust's history is crucial for appreciating its design principles, which emphasize safety, speed, and concurrency without sacrificing the low-level control over system resources. Why Rust for blockchain? Rust is a system programming language that is being increasingly favored for blockchain development. This is due to several of its features, such as memory safety, concurrency, and performance. The following are reasons why Rust is particularly suitable for blockchain applications. Rust's ownership model prevents memory safety issues, a crucial feature when dealing with blockchain systems that require high security to protect financial transactions. The language's emphasis on concurrency allows for efficient processing of multiple transactions and interactions with the chain. Rust's performance is comparable to C++, making it fast enough for the demands of a blockchain's real-time processing needs. Furthermore, Rust's rich type system and pattern matching promote writing clear and predictable code, reducing the chances of bugs and vulnerabilities in blockchain applications. Rust syntax and semantics. In Rust, variables are immutable by default. When a variable is immutable, once a value is bound to a name, you can't change that value. To make a variable mutable, the mute keyword is used. In this snippet, x is an immutable variable bound to the value 5. Trying to change the value of x later in the code would result in a compilation error. On the other hand, y is a mutable variable. The mute keyword before the variable name y allows us to change the value of y after it is declared. We increment it by 1 using the plus equals operator. Ownership, borrowing, and lifetimes. Ownership is a core feature of Rust that enables memory safety without a garbage collector. Each value in Rust has a variable that's called its owner. There can only be one owner at a time, and when the owner goes out of scope, the value is dropped automatically. In this example, the string s is owned by the variable s. When we pass s to the function takesOwnership, the ownership is moved to the parameter someString, rendering s invalid for future use. In contrast, the integer x is copied when passed to the function makesCopy, because types like integers that have a known size at compile time are stored on the stack and are copy, meaning they can be used after being passed to the function. Error handling in Rust. In Rust, the result type is a powerful enum for error handling that can return either a successful value, OK, or an error, It is defined as result t, e, where t is the type of the value returned in the case of success, and e is the type of the error returned in case of failure. In this code snippet, we define a variable result of type result i32 and str, which is an instance of OK containing the value 200. We then use a match statement to pattern match on that result. If the result is OK, it will print the success message along with the value. If it were an error, it would print the provided error message. The result type is commonly used for functions that can fail, where the OK variant signifies a successful execution and the error variant indicates failure. Using Cargo, Rust's build system, and package manager. Cargo is the official Rust package manager and build system. It not only manages dependencies for your Rust projects, but also compiles your code, as well as running tests and benchmarks. To get started, you'll need to install Rust, which includes Cargo by default. Once installed, we can begin by creating a new project. The given command creates a new Rust project with the name MyBlockchain project. When executed, Cargo sets up a new directory with the same name, containing a cargo.toml file, which is the configuration file for the project, and a src directory that houses a main.rs file, which is the entry point for a Rust application. This command initializes a new Git repository if Git is available on your system. Hash functions, 56. Hash functions are cryptographic algorithms that take an input and produce a fixed-size string of bytes. The output is typically a digest that appears random. A key feature of cryptographic hash functions is that they are collision-resistant. It should be hard to find two different inputs that produce the same output hash. SHA-256 refers to the secure hash algorithm 256-bit and is a variant of the SHA-2 family designed by the NSA. It is widely used in blockchain to ensure data integrity. The code demonstrates how to calculate a SHA-256 hash in Rust using the SHA-2 crate. Here, we define a function calculate SHA-256 that takes a string slice reference as input. We create a new SHA-256 object and then use update to feed our input into the hasher. After updating the hasher with the desired input, we call finalize to complete the hashing process, which returns the hash result. Finally, the hash is formatted into a hexadecimal string representation using format with X. Public key cryptography. Public key cryptography, also known as asymmetric cryptography, is a fundamental concept in the security of blockchain technology, enabling secure communication, digital signatures, and key exchanges. It uses a pair of keys, a public key, which can be shared openly, and a private key, which is kept secret. Together, they allow for secure interactions such as encrypting and decrypting messages, or creating and verifying digital signatures. The code provided demonstrates the basic use of public key cryptography with the RSA algorithm in Rust. The RSA crate's RSA private key is used to generate the private key, which is kept secret, and RSA public key is derived from the private key, which can be made public. We use OSRENG from the RAND crate to generate randomness needed for key generation and encryption. The chosen key size is 2048 bits for security. The encryption is done using OAEP padding with SHA-256 hashing, and the decryption must use the same padding scheme. The encrypt function of the public key encrypts a message, and the decrypt function of the private key decrypts it. The final assertion checks that the decrypted data matches the original message. Digital signatures, e.g. ECDSA. Digital signatures are a cryptographic tool used to ensure authenticity and non-repudiation. In blockchain, they allow participants to sign transactions, proving ownership of a blockchain address without revealing the private key. The elliptic curve digital signature algorithm, ECDSA, is commonly used for this purpose. It is based on the principles of public key cryptography, where a private key signs the data and a corresponding public key validates the signature. Let's create a simple example in Rust to demonstrate how ECDSA can be used to sign and verify a message. The provided code snippet is written in Rust language and uses the K256 crate, which enables ECDSA signing and verification for the CP256K1 curve, common in blockchain technologies. First, a new ECDSA key pair is generated using OSRENG for secure random number generation, ensuring the private key, signing key, is kept secret. The corresponding public key, verify key, is derived and serialized to bytes to share publicly. A message is created and signed with the private key, resulting in an ECDSA signature. Finally, the validity of the signature is checked using the public key, ensuring that the message was signed by the holder of the private key, and the result of verification, true or false, is printed. This process ensures the authenticity and integrity of the message. Merkle trees and Merkle proofs. A Merkle tree is a fundamental component in blockchains for efficiently summarizing and verifying the integrity of large sets of data. The tree consists of a binary structure where each leaf node represents a hash of a data block, and each non-leaf node is a hash of its children's hashes. Merkle trees help in minimizing the amount of data needed to verify the contents of the block. The code represents a basic Rust function to create a Merkle tree. The hash pair function takes 2 byte slices, hashes them using SHA-256, and returns the resulting hash. Build Merkle tree takes a vector of data blocks, treats each as a leaf node, and repeatedly hashes pairs of nodes to build up the tree. If there's an odd number of nodes at a level, it duplicates the last one, a common strategy to handle unbalanced trees. The process continues until there is one root hash representing the top of the Merkle tree. Blocks and the blockchain. A blockchain consists of a series of blocks, each containing data, the hash of the block, and the hash of the previous block, creating a linked chain. Each block's hash is calculated based on its contents, ensuring the integrity of the entire chain. If one block's data is altered, its hash changes, breaking the chain's link, which can be detected and rejected by the network participants. In the provided Rust code, a block struct is defined with fields for the index, timestamp, data, previous hash, and the hash of the block itself. The new function is an associated function, similar to a static method that creates a new block given an index, timestamp, data, and the hash of the previous block. The create hash function stub, not fully implemented here, represents the logic to generate a hash for the block. Each block's hash must include the information of the entire block, so any tampering with the data would result in a different hash, breaking the chain's integrity. Transactions and UTXO model. In the blockchain context, a transaction represents a transfer of value between participants. The UTXO, unspent transaction output model, treats these transfers like banknotes exchanged in cash transactions. Each transaction input is linked to a previous unspent output, and each transaction produces new outputs that can be used as inputs for future transactions. We'll define a basic structure for a transaction in Rust. We've created 3 structures defining the components of a transaction. The transaction input structure contains a reference to a hash of the output from a previous transaction and a signature to prove ownership. The transaction output structure includes the value, representing the amount of currency, and public key hash, which ties the output to a specific entity. The transaction structure aggregates multiple inputs and outputs, representing a complete E-key, potentially multi-party transaction. The VEC typology allows for a variable number of inputs and outputs, providing the flexibility needed for complex transactions. Blockchain state. In the context of a blockchain, the state refers to the current status of all recorded data, which includes account balances, contract code, and contract states. The blockchain state needs to be consistent and is often stored in a way that allows quick verifications and updates. In Rust, we might use structs and other data types to represent the state. This Rust code defines a blockchain state struct that holds a hash map with account addresses as keys and their corresponding balances as values, U64 type for simplicity. We provide a constructor new that initializes an empty state. The getBalance method retrieves the balance of a given address, returning 0 if the address isn't in the state. The updateBalance method inserts or updates an address's balance. It's important to manage these operations atomically to ensure consistency of the blockchain state, but this simple example does not include concurrency or transaction handling logic. Implementing hash functions in Rust. In blockchain applications, hash functions are crucial for the integrity and security of the data. SHA-256 is a commonly used cryptographic hash function. Rust has a crypto crate that provides an implementation of SHA-256. Below is an example demonstrating how to use SHA-256 in Rust. The code first brings into scope the SHA-256 type and digest trait from the SHA-2 crate. In the main function, we create a mutable variable hasher as an instance of SHA-256. The update method is used to feed bytes b hello world into the hasher. Finally, the finalize method completes the hashing process and returns the hash result. The output is formatted as a hexadecimal string and printed to the console. Creating a basic block structure. In a blockchain, the basic structure is the block. It typically consists of data, a hash, which serves as a unique identifier, and the hash of the previous block to establish a secure link. Let's define a simple block structure in Rust, putting focus on struct definitions and how we might structure the data involved. The code snippet provides a definition for a block struct in Rust, which contains the basic elements of a blockchain block: index, timestamp, data, previous hash, and hash. The implementation of a new block uses a constructor method new, which takes parameters for all fields except the hash, which is initially set to an empty string as a placeholder. This method can later be expanded to include computing the hash of the block based on its content. Handling transactions in Rust. In a blockchain, transactions are the actions that change the state of the ledger. Handling transactions in Rust involves creating structures to represent transactions and logic to process them. We will define a transaction struct, a block struct that will contain transactions, and a simple blockchain to hold the blocks. We'll also write a function to add a new transaction to a block. In the code, we define a transaction struct with sender, receiver, and amount fields to represent a transfer between two parties. The block struct contains a priv block hash pointing to the previous block in the chain and a transactions vector to hold the transactions. Next, we implement a constructor new for creating a new block, which takes the previous block's hash as an argument. A method addTransaction is also defined in the block implementation, which takes a transaction instance and adds it to the transactions vector. Blocks can now contain multiple transactions, and we can dynamically add new transactions to each block. Managing blockchain state. In a blockchain system, the state refers to all of the data that is stored on the blockchain. This includes things like account balances, smart contract code, and any other data that can change over time. Managing blockchain state efficiently is crucial for ensuring the integrity and performance of the blockchain. We will go over how to structure and manage the blockchain state using Rust, which is well suited for these tasks due to its guarantees on memory safety and concurrency control. In the code example provided, the blockchain struct has two members, chain and current transactions. The chain is a vector of block structs representing the actual blocks in the chain, and current transactions is a vector of transaction structs representing transactions that have not been included in a block yet. The blockchain's new function initializes these vectors as empty. The addBlock method takes a block, which is then appended to the chain. The addTransaction method adds a new transaction to the current transactions vector and returns the index of the block that the transaction will be part of, which is the next to be created. This basic structure and its accompanying methods form the foundation of managing the blockchain state. But to become a fully functional blockchain, more functionality is required, including transaction verification, block creation, and consensus algorithms. Proof of work. Proof of work, POW, is a consensus mechanism that is used to secure many blockchain networks. It involves solving a cryptographic puzzle that requires computational effort. Miners compete to solve the puzzle, and the first one to find the solution gets the right to add a new block to the blockchain. This mechanism provides security as it makes it expensive and time-consuming to attack the network. Below is a simplified Rust function that represents the concept of proof of work, where the goal is to find a hash that starts with a certain number of 0 bits. The provided Rust code defines a function called proof of work, which takes two arguments: prefix zeros, specifying the number of leading 0 bits that the hash must have, and data, a string slice representing the data to be hashed. Inside the function, a nonce is iterated over in a loop to change the hash output until a hash that satisfies the condition, hash with the required number of leading 0 bits, is found. The SHA-2 crate is used for hashing. The loop runs indefinitely until the condition is met. When the right nonce is found, the loop breaks and the nonce value is returned as proof of the computational work done. Proof of stake. Proof of stake, POS, is a type of consensus algorithm by which a cryptocurrency blockchain network aims to achieve distributed consensus. Unlike proof of work, which requires miners to perform complex calculations to mine a block, POS chooses validators based on the number of coins they hold and are willing to stake or lock up as a form of security. Validators are selected to create a new block based on various combinations of random selection and wealth or age, i.e. the stake. Let's construct a basic structure in Rust where we represent participants who can become validators in a POS system. In the provided Rust code, we define a struct named validator, which represents a participant in the network. Each validator has an ID and a stake amount, The stake indicates how much currency the validator is willing to lock up to participate in the validation process. The impl block contains a constructor new to create a new validator. The function selectValidator takes a slice of validator references and uses an iterator to find the validator with the highest stake, mimicking a simplistic stake-based selection mechanism. This participant would theoretically have a higher chance of being chosen as the validator for the next block in an actual POS implementation. This is a fundamental concept in proof of stake. Choosing a consensus mechanism for your blockchain. A consensus mechanism is vital for maintaining the integrity and security of a blockchain. It ensures all participants agree on the blockchain's state, prevents double spending, and secures transactions against tampering. In this section, we'll explore different consensus mechanisms and how to select one suitable for the blockchain we're developing using Rust. The code provided defines an enumeration consensus mechanism that lists different types of consensus algorithms that can be implemented in a blockchain system. It also contains a method choose_mechanism that maps a string identifier to the corresponding consensus mechanism. This method can be used to select the consensus mechanism based on user input or configuration settings. In a real-world scenario, the chosen consensus algorithm will inform the implementation details of the blockchain, such as how blocks are proposed, validated, and added to the chain. Implementing consensus mechanisms in Rust. In blockchain systems, consensus mechanisms are algorithms used to achieve agreement on a single data value among distributed processes or systems. They are essential for maintaining the integrity and consistency of the blockchain. Implementing a simple proof of work, POW consensus in Rust, involves creating a function that attempts to find a hash of a block with a certain number of leading zeros, also known as the difficulty. Below is a basic implementation of the POW algorithm using Rust. The proof of work function takes a reference to the previous block's hash, a string of transactions, and the difficulty level as inputs. It initializes a nonce, a number only used once, and enters a loop to calculate the hash of the concatenated string of the previous hash, transactions, and the current nonce. The loop continues until it finds a hash that satisfies the difficulty condition, i.e., has a certain number of leading zeros. If the condition is met, the function returns the nonce and the valid hash. The SHA-2 crate is used here for hashing purposes. To use SHA-2, include it in your cargo.toml. This code exemplifies a basic proof-of-work consensus algorithm, which is commonly used in many blockchain implementations to ensure security and prevent double spending. Peer-to-peer network basics. A peer-to-peer, P2P network is a decentralized communication model where each party, called a peer, has equivalent capabilities and responsibilities. This is different from traditional client-server models, where the communication is between the centrally serviced clients and a server. P2P networks are commonly used in blockchain systems to ensure a distributed manner of data sharing, where each node can potentially contribute to the network's functionality. Rust, with its focus on safety and concurrency, provides a strong foundation for building reliable P2P networks. In this Rust code snippet, we're setting up a basic TCP server, which could be the first step in creating a P2P network. We use TCP listener to bind to a local IP address and port. The incoming method returns an iterator over the incoming connections. For each incoming TCP stream, we call handle client, a function where you'd typically implement communication logic. The match statement is used to handle the result of the incoming connections. If the connection is successful, OK variant, we handle the client, otherwise we handle the error variant. This code doesn't implement the full P2P functionality, but establishes the foundation for network communication. Gossip protocols. Gossip protocols, also known as epidemic protocols, are used to ensure information is disseminated efficiently and reliably throughout a distributed system. The concept is akin to how gossip spreads in social networks. Nodes randomly share information with each other until all nodes are aware of the information. Rust's robust concurrency features make it an excellent choice for implementing such protocols. The provided Rust code is a simplistic representation of a gossip protocol. It has a gossip function, that takes in a mutable slice of peers and a message to disseminate. The scene hash set keeps track of which peers have received the message, identified uniquely by their memory address cast to a usize. Using the rand crate, it randomly picks peers from the list to send the message to, as indicated by pseudocode, ensuring that the message is eventually sent to all peers. The loop continues until all peers are seen, i.e., have presumably received the message. Building a P2P network in Rust. In this section, we will go through the basics of setting up a peer-to-peer P2P network in Rust. We'll use the libp2p library, which provides a solid foundation for P2P networking. First, we set up a simple node that can send and receive messages. Note that error handling is omitted for brevity. In the provided code, we first import the necessary modules from libp2p, such as identity for key generation, swarm to manage the network state, network behavior to define our custom behavior, and others for MDNS and FloodSub protocol capabilities. We then define a myBehavior struct that implements the network behavior trait, enabling us to handle events from the FloodSub and MDNs components. In the implementation of network behavior event process for FloodSub event, we specify how to handle incoming messages simply by printing them to the console. Next, we generate a new edi25519 key pair for our local node and derive a peer ID from it. We set up the transport layer, the means by which peers communicate, that libp2p could use during development. Then we combine our myBehavior, the transport, and the local peer ID into a swarm, which encapsulates the whole network state. The swarm builder is used to build the swarm, and it will execute async tasks using the Tokio runtime. Implementing network messages and communication. In a decentralized blockchain system, peers communicate over a network to exchange data such as transactions and blocks to maintain consensus. Network messages are integral to this. Using Rust, we can create well-defined structures for our messages and use serialization to prepare them for transmission. Below is a simplified version of how you might implement basic messaging between nodes in a P2P blockchain network. In the code snippet above, we define an enum called message that represents the different types of messages that nodes can send to each other. This enum includes variants for new transactions and blocks, as well as a request for the current blockchain. The transaction and block structs represent the data structures for transactions and blocks, respectively. We use the Serde library for serializing and deserializing these structs, since network communication involves sending data in a byte format. This code serves as a foundation. You would need to integrate actual networking code to send and receive these messages using a Rust networking library like Tokio or async.std. What are smart contracts? Smart contracts are self-executing contracts with the terms of the agreement directly written into lines of code. They run on a blockchain, which enables them to operate without a central authority, and their transactions are trackable and irreversible. Smart contracts allow for the automation of processes, ensuring that once predetermined conditions are met, the contract will execute the corresponding actions. While smart contracts are mostly associated with the Ethereum blockchain, which introduced a Turing-complete language for writing them, the concept is applicable across various blockchain platforms. The essential feature of a smart contract is its ability to automate, enforce, and verify the performance of a contract without intermediaries, based solely on the code's logic and input conditions. Running smart contracts on a blockchain. In a blockchain context, smart contracts are self-executing contracts, where the terms of the agreement are directly written into lines of code. They run on a decentralized network, such as Ethereum, and are immutable once deployed. Rust is gaining popularity for writing smart contracts due to its safety and performance. In this example, we'll look at a simple Rust smart contract that could be compiled to WebAssembly, WASM, and deployed to a blockchain that supports WASM execution, like the Parity Substrate framework. The provided Rust code showcases how a simple smart contract for a blockchain may look. The /no_std attribute indicates that the standard library is not linked because most smart contract platforms don't provide a full standard library due to sandboxing restrictions. We utilize pwasm_std, a standard library for developing WASM smart contracts. The call function is what gets executed when someone calls the smart contract, for instance, to perform a transaction like transferring tokens. The deploy function is called once when the contract is initially deployed to the blockchain, mainly to perform setup tasks such as initializing contract state. Note that this is not a complete contract, it's a template to illustrate the concept of smart contract functions in Rust. WebAssembly for blockchain smart contracts. WebAssembly is a binary instruction format that enables high-performance applications on the web and is now increasingly used for blockchain smart contracts. It's designed to be portable and efficient, making it a good fit for the constrained environments where smart contracts run. We do not have a code snippet here, as this is a conceptual overview. YSM provides a compilation target for languages like Rust, allowing developers to write smart contracts with familiar tools and then compile them into a format that's efficient for blockchains to execute. The performance and security benefits stem from YSM's tight binary format, which runs close to native execution speed and is sandboxed to prevent unintended interactions with the host system. Developing smart contracts in Rust. Before starting to develop smart contracts in Rust, you need to set up your development environment. This includes installing Rust, Cargo, Rust's package manager, and any other dependencies such as the WebAssembly (WASM) toolchain, since smart contracts for blockchain are often compiled to WASM to ensure compatibility and security. The first command installs Cargo Generate, a developer tool for creating a new Rust project template. The second command adds the wasm32-unknown target to Rust, which allows you to compile Rust code to WebAssembly, an essential step for developing blockchain smart contracts. Creating and managing tokens. In the context of blockchain, tokens are digital assets that can represent ownership or a right to services within a network. In Rust, creating and managing tokens involves defining a structure that represents the token and implementing functions to manage token balances and transfers. This Rust code defines a token struct with fields name, symbol, and total supply to represent a cryptocurrency token. The derive attribute automatically implements the debug, clone, and partial eq traits, which are useful for debugging, copying, and comparing tokens, respectively. The implementation of token includes a constructor method new to create a new token and a transfer method to handle the transfer of tokens by subtracting the amount from the total supply if enough tokens are available. If the transfer is successful, it returns true. Otherwise, it returns false to indicate failure due to insufficient tokens. Understanding incentives in blockchain. Incentives are crucial in blockchain networks, ensuring that participants are motivated to act in the best interest of the network. They are designed to encourage specific behaviors, such as validating transactions, maintaining security, or contributing to the network's development. These incentives often come in the form of tokens or cryptocurrencies, which can have various attributes and mechanisms for distribution. The code defines a struct blockchain incentive that represents the incentive system of a blockchain. It includes a field for the reward per block to specify how much reward is given out for each mined block, and a vector of validators to store the list of entities eligible for rewards. The new function initializes the incentive system, and add validator allows adding new validators. The distribute rewards function simulates the process of distributing rewards evenly to all validators. Though in an actual blockchain, rewards might be distributed based on different criteria, such as stake size, number of blocks validated, etc. This basic framework can be expanded upon to simulate more complex incentive mechanisms within a blockchain network. Designing a token economy in your blockchain. Designing a token economy entails creating a self-sustaining economic system that guides the issuance, distribution, and management of tokens within a blockchain. Tokens can incentivize certain behaviors, represent ownership or access rights, and facilitate transactions. To design this system, you must consider the total supply of tokens, their distribution mechanisms, the incentive structures for participants, and the governance rules that dictate how tokens can be used or exchanged. The given code snippet defines a basic structure for a token economy within a Rust implementation of a blockchain. The token economy structure includes fields for total supply, distribution strategies, incentive structures, and governance rules. This sets up the foundational elements that will govern how tokens are created, allocated, and used within the blockchain. The code presumes that additional types such as distribution strategy, incentive, and governance will be defined elsewhere in the codebase, and these will detail how tokens are distributed, e.g., through mining or staking, how users are incentivized, e.g., through transaction fees or rewards, and the rules that govern token usage. This structure might then be used to initialize the token economy in the blockchain's Genesis block or through a smart contract. RPC and RESTful APIs. In a blockchain context, APIs are interfaces that allow external applications to communicate with the blockchain network. Two commonly used types of APIs are Remote Procedure Call, RPC, and Representational State Transfer, RESTful APIs. RPC APIs in blockchain allow clients to directly call methods on the blockchain nodes as if they are local functions. RESTful APIs, on the other hand, use standard HTTP methods, GET, POST, PUT, DELETE, to interact with the blockchain resources, and are often easier to integrate with web applications. The given Rust code snippet demonstrates a simple, RESTful API endpoint for a blockchain application using the Warp framework. It creates an asynchronous main function and utilizes a Warp filter to define a GET endpoint at the path/blockchain. When this endpoint is hit, the retrieve blockchain info function is called to fetch and return the current state of the blockchain as JSON. The Warp serve function is used to host this API on localhost 127.00.1 at port 3D30. The retrieve blockchain info function is stubbed out to return a static JSON response, which in a real implementation would fetch the actual blockchain data. Exposing blockchain data via APIs. Exposing blockchain data via APIs involves creating accessible endpoints for users and external systems to interact with the blockchain. This typically involves setting up a RESTful API, since REST is widely used for its simplicity and compatibility with web technologies. In the context of a blockchain written in Rust, we'd use web frameworks like Rocket or Actix to expose HTTP endpoints that provide access to blockchain data, such as block details, transaction history, and wallet balances. The code snippet provides a basic Actix example that sets up a web service with a single GET endpoint to fetch blockchain data. The GET blockchain data function is marked async and returns an implementation of responder, which in this case is an HTTP response. The response is a JSON object. The HTTP server new closure initializes an instance of app that's configured with a route at /blockchain that handles GET requests by invoking GET blockchain data. The server binds to the address 127.0.1 AD and starts serving requests when run is called. In a real blockchain application, this function would include logic to retrieve and return the actual blockchain data. Cross-chain communication. Cross-chain communication refers to the ability of one blockchain to access, send, receive, and understand data and assets from another blockchain. This concept is essential in creating an interoperable ecosystem where different blockchains can work together seamlessly, enabling a more connected and functional blockchain environment. While Rust code is not provided for this concept, since it is an architectural aspect of blockchain rather than a specific codebase, it's important to understand that cross-chain communication is implemented through mechanisms such as blockchain bridges, sidechains, and Layer 2 solutions. These systems often involve smart contracts, relay or oracle services, and consensus mechanisms to securely manage and verify transactions and state changes across chains. Unit testing in Rust. In Rust, unit tests are written in the same files as the code they are testing. They are typically placed in a module named tests that is annotated with the CFG test attribute to indicate that the module should only be compiled when running tests. Unit tests make use of the test attribute to denote test functions and utilize various assert macros to verify code behavior. In the provided code, we define a simple function add2 that adds 2 to its argument. Next, we declare a test module with #cfg_test, indicating that this module is for testing purposes and should not be included in the final build. Inside the module, we import everything from the parent module using useSuperSAR. Then we declare a test function it adds 2, marked with the test attribute. The test function uses the assert EQ macro to assert that the result of calling add2 with the argument 2 equals 4. When we run cargo test, the test suite will run this function, and if the assertion holds true, the test will pass. Integration testing for blockchain. Integration tests assess the interaction between multiple parts of your blockchain system, such as how blocks are added to the chain, or how your network nodes communicate. In Rust, integration tests are typically placed in a directory named tests at the root level of your project. Each file in the tests directory is compiled as a separate crate. Below is a simple integration test example for a blockchain that tests the ability to create a new block and add it to the chain. In this code snippet, we define a module, integration tests, with the #fgtest attribute to specify that this module is for testing purposes. We then create a test called test block creation and chain addition using the test attribute. Inside this test, we instantiate a new blockchain, create a block with some dummy data, and add it to the blockchain. Lastly, we assert that the length of the blockchain's blocks vector should be 2, taking into account the genesis block that is assumed to be added when the blockchain is instantiated. This integration test verifies our block creation and addition logic. Auditing smart contracts. Auditing smart contracts is a crucial step to ensure the security and integrity of the code that will be deployed on a blockchain. Smart contracts are immutable once deployed, making audits essential to catch any potential vulnerabilities beforehand. This process typically involves reviewing code, checking for common vulnerabilities, and ensuring that the contract behaves as intended. While Rust itself isn't directly used for writing smart contracts for platforms like Ethereum, which primarily uses Solidity, it can be used to write smart contracts for blockchains like Solana or the Polkadot ecosystem. Auditing in this context does not necessarily mean a specific code example, but a process. It often includes manual code review to understand business logic, automated tools to find common vulnerabilities, and formal verification methods that mathematically prove properties of smart contracts. Ensuring rigorous testing can significantly reduce risks associated with smart contract deployment. Security best practices. When developing a blockchain in Rust, it is critical to follow security best practices to ensure the integrity and safety of the chain. Given Rust's strong type system and ownership model, it already provides a good foundation for building secure applications. Below, we'll touch upon some key practices to implement in your blockchain project. Although Rust provides many safety guarantees at compile time, there are still runtime security considerations to be aware of. For instance, validating input data thoroughly to prevent injection attacks, utilizing Rust's built-in result type for error handling to prevent panics and potential DOS attacks, managing dependencies carefully to avoid pulling in insecure crates, and finally, conducting regular audits and security reviews of your code to identify and patch vulnerabilities. It's also important to use cryptography wisely, ensure that private keys are never exposed, and use Rust's zero-eyes crate to clear sensitive information from memory. These measures help maintain the robustness and security of your blockchain. Deploying a Rust-based blockchain. Deploying a Rust-based blockchain involves compiling the Rust code into a binary, configuring the network, and setting up the infrastructure to run the blockchain nodes. We'll look at how to build the code and prepare it for deployment on a basic level. The given command is used to compile Rust code into a release build, which optimizes the binary for performance. Cargo is Rust's build system and package manager. When you run cargo build release, it creates an executable in the target release directory of your project. The -release flag is vital for blockchain applications as it minimizes the binary size and maximizes the performance, which can be critical for a performant and scalable blockchain system. Once the build is completed, the binary can be transferred to the server or node where the blockchain will operate. Version upgrades and forks. Version upgrades are crucial for blockchain maintenance and evolution. They can be implemented as soft forks, which are backward compatible, or hard forks, which are not. In Rust, Upgrades can be managed using cargo's versioning or by implementing upgrade mechanisms within the blockchain protocol itself. Let's create a function to demonstrate a simple versioning mechanism where nodes can adopt new features or protocol changes without disrupting the network. The code defines an enum blockchain version to represent different versions of our blockchain. A struct blockchain node represents a node in the network with a version field. The upgrade method is implemented for blockchain node, allowing the version to be updated. This structure allows our blockchain to recognize and switch between different versions, providing a foundation for implementing soft forks. During a soft fork upgrade, the node can switch to a higher version while still being able to communicate with nodes on the lower version, ensuring backward compatibility. Monitoring and maintenance techniques. In the context of a Rust-based blockchain, effective monitoring and maintenance are crucial for ensuring network stability, performance, and security. Monitoring involves tracking the system's health, performance metrics, and potential security threats in real time. Maintenance involves updating the code, fixing bugs, and improving system performance. One approach to monitoring is using logging and metrics collection tools. Here's how we can integrate a simple logging mechanism using the log crate in Rust. The code snippet demonstrates the use of the log crate, which provides macros for logging at different levels, e.g. info, warn, error. By calling endLogger init, we initialize the logging system, which by default will log all info level and above logs. Implementing logging throughout your blockchain code allows you to monitor its operation and quickly identify issues when they occur. The info macro logs useful information like the addition of a new block, while warn logs unexpected behavior that might require attention. Logs can later be analyzed to track the system's performance and detect abnormal patterns that may indicate problems. Zero-knowledge proofs. Zero-knowledge proofs, ZKPs, are cryptographic methods that allow one party, the prover, to prove to another party, the verifier, that a certain statement is true, without revealing any additional information besides the validity of the statement. They are particularly useful in blockchain for maintaining privacy and are a fundamental component of privacy-oriented cryptocurrencies like Zcash. In this example, we will show a simplified concept of a zero-knowledge proof using the zk-SNARKs approach in Rust, which is not a complete ZKP system, but will give you a basic idea of how such a system might be structured. In this simplified Rust code snippet, we're setting up the basic structure for a zk-SNARK circuit using the Bellman crate, which is a library for building zk-SNARKs in Rust. The myCircuit struct would represent our zero-knowledge proof circuit, with various elements, in this case just A, representing inputs to the circuit. The synthesize function is where the actual constraints of the zero-knowledge proof would be programmed. The elements and constraints ensure the prover can prove they know certain information without revealing the information itself. Finally, in the main function, one would normally create an instance of the circuit and generate a proof, but the code for that has been omitted for brevity. Interplanetary File System, IPFS. The Interplanetary File System, IPFS, is a protocol and network designed to create a content-addressable, peer-to-peer method of storing and sharing hypermedia in a distributed file system. Unlike traditional file serving and sharing methods, which are location-based, IPFS addresses content by what it is, rather than where it is, thereby making the web faster, safer, and more open. In Rust, one can use the IPFS API crate to interact with IPFS. In the provided Rust code, we initialize an instance of a PFS client from the IPFS API crate. An asynchronous main function is created with Tokyo main, which allows us to make asynchronous calls. Using the IPFS client, we add some data, in this case, a simple string hello world, to the IPFS network. This is accomplished by wrapping the string in a cursor, which implements read and async read, allowing the IPFS AP crate to consume the data stream and send it to an IPFS node. The add method is then called asynchronously, and the result is handled. On success, it prints out the unique hash assigned to the content. On failure, it prints an error message. This hash can be used to access the data from any IPFS node. Sharding mechanisms for scalability. Sharding is a popular technique used in blockchain technology to enhance the scalability of a network. It works by partitioning the blockchain into smaller units called shards. Each shard contains its own state and transaction history, effectively dividing the processing and storage workload across a network of nodes. By doing this, sharding increases the capacity of the network to process transactions in parallel, leading to improved overall system performance. However, implementing sharding in a blockchain system introduces complexity in areas like inter-shard communication, security, and data consistency. Here's a simple Rust code that demonstrates the basic concept of creating multiple shards in a blockchain-like system. The presented code defines a basic structure for implementing shards in Rust. The shard struct represents a shard with an ID and a list of transactions. A transaction struct represents a transaction with a sender, recipient, and value attributes. The shard struct also has an addTransaction method to add a transaction to the shard. In the main function, we instantiate two shard instances, representing two separate shards in a hypothetical blockchain network. We then add a transaction to each shard. This simple representation serves as a starting point for understanding how sharding can allow transactions to be processed in parallel, potentially on different nodes of a blockchain network. The actual implementation of a sharded blockchain would be more complex and involve various additional concepts, such as cross-shard communication, state management, and consensus algorithms. Off-chain solutions, e.g., Lightning Network. Off-chain solutions are mechanisms that enable transactions to be executed without having to be recorded on the blockchain immediately. This approach helps to alleviate the scalability constraints that blockchains naturally face. The Lightning Network is a prominent example, specifically designed for Bitcoin, which allows users to create payment channels between each other for fast and low-cost transactions. These transactions are settled on the blockchain after the channel is closed. The following Rust code is a simplified representation of establishing a payment channel, which is a fundamental operation within off-chain networks like the Lightning Network. In the given Rust code snippet, we define a function called establishPaymentChannel that simulates the process of opening a payment channel. This function takes three parameters: the sender, the receiver, and the amount in satoshis. It returns a string message indicating that the channel is established. In an actual Lightning Network implementation, there would be cryptographic processes for securely establishing the channel, handling conditional payments, and ensuring that the channel can be settled on the blockchain once it's closed. The main function demonstrates using the establishPaymentChannel function by creating a payment channel from Alice to Bob with an amount of 10,000 satoshis. Designing your own blockchain solution. Designing your own blockchain solution involves understanding the core components of a blockchain: blocks, transactions, hashing, consensus mechanism, and a network protocol. We will build a simplistic, proof-of-concept blockchain in Rust to illustrate these components and their interaction. Rust provides memory safety and concurrency advantages, which are beneficial for blockchain development. The code above represents a basic blockchain structure in Rust, where a block struct is defined with relevant attributes such as index, timestamp, data, previous hash, and hash. The new associated function takes the parameters needed to create a new block and calculates the block's hash based on those values using a placeholder function calculateHash. This forms the building block of a blockchain, with each block being linked to the previous one via the previous hash attribute, allowing the creation of an immutable chain of records. Implementing a custom feature set. When creating a blockchain from scratch, one of the key aspects is to define a set of features that distinguishes your blockchain. A feature set can include custom transaction types, consensus mechanisms, smart contract capabilities, or a special algorithm for balancing between scalability and security. In Rust, we implement these custom features by writing modules that encapsulate the desired functionality. Below, we'll be writing a module to implement a simple custom feature for our blockchain, a reward transaction for miners. The code defines a module named blockchain that contains a struct reward transaction. which models a reward given to miners as part of the consensus protocol for block mining. The struct has two fields, to, which is the address of the miner, and amount that specifies the reward. We also implement new as an associated function to create instances of the reward transaction. Furthermore, a test module named tests with a single unit test create reward transaction is added to verify that reward transactions are created correctly. The test checks that the to field matches the intended recipient's string and the amount is correct. By grouping related features in modules, you maintain organized and modular code, which is a best practice in Rust. Testing network and performance. In the context of blockchain development, testing the network and performance involves confirming that the blockchain operates correctly under various conditions and scales efficiently. In Rust, we can use testing frameworks and benchmarking tools to assess the performance of our blockchain network. It's key to ensure that the blockchain maintains its integrity and consensus mechanisms work properly as the network grows and is subjected to different stresses. The Rust code snippet uses the criterion crate to create benchmarks for the blockchain project. The blockchain performance function defines a benchmark that simulates transactions on the blockchain. C.bench function takes a name for the benchmark and a closure that contains the actual benchmarking loop. Inside this loop, bdata continuously calls a hypothetical transaction simulation function to mimic the processing of transactions, and blackbox is used to prevent the compiler from optimizing the code during tests, ensuring a realistic performance measurement. The benchmark is added to a criterion group and then executed with criterion main, producing a report of the performance metrics. Preparing documentation and presentation. Good documentation is crucial for any project, especially open source ones like blockchain. It serves as a guide for users and contributors, explaining how the system works and how to use or improve it. The code block provided exemplifies a Rust documentation comment that would be placed at the top of a module in your blockchain project. This style of comment, indicated by 3 slashes, is used to generate user-facing documentation using Rust's documentation tool, RustDoc. The comment outlines the purpose and basic use of the module and includes an example of how to instantiate and use the blockchain structure, assuming it's part of a library named MyBlockchain. When writing documentation, ensure it's clear, concise, and provides practical examples.